Well, hello everyone. In this video lecture, we'll be solving problem number 1.47 of the book Aptitude Test Problems in Physics by S.S. Krotov. On a quick note, links for my previous videos are given in the description below, and if you haven't subscribed yet, then subscribe now for more such videos. Without wasting any more time, let's begin solving. So the question says, a weightless rod of length L with a small load of mass m at the end is hinged at point A and occupies a strictly vertical position touching a body of mass m. A light jerk sets the system in motion. So at t is equal to 0, a light jerk sets the system in motion, bringing the load m towards the negative y-axis, which of which the rod forms an angle alpha with the horizontal at the moment of separation from the body M, and the body M moves towards the x-axis after the jerk. Coming back to the question, for what mass ratio m by m, will the rod form an angle alpha equals pi by 6 with the horizontal at the moment of the separation from the body? What will be the velocity u of the body at this moment? So we have to find the velocity u of body m at the moment of separation from the load m. Friction should be neglected. So friction is absent in this system. As long as the load touches the body m, the velocity of the body is equal to the horizontal component of the velocity of the load. So Vh, the horizontal component of the velocity of the load, that is m, equals u, the velocity of the body m. And the acceleration of the body is equal to the horizontal component of the acceleration of the load. And the horizontal component of the acceleration of the load, that is ah, as shown here, ah equals the acceleration of m. And we know that the total acceleration is the tangential acceleration plus the centripetal acceleration. This is for the load m. And the horizontal component of the acceleration of load m is at sine alpha, as this is the alpha, this is the angle, at sine alpha, plus minus of ac cos alpha, ac cos alpha in the negative direction, which gives us a at sine alpha minus v square by l cos alpha, as ac, the centripetal acceleration is v square by l being the radius of which the load m forms while it is falling, while pushing the body m towards the right direction. The body also has the same acceleration. We can write the equation of motion for the body as n, as n is the only factor that is moving the body towards the right direction, which is mah, which gives us m at sine alpha minus m v square by l cos alpha, where n is the force of normal pressure exerted by the load on the body. At the moment of separation from the body, n equals 0. This is the condition for separation, n equals 0. and which gives, this is equation 1. After n equals 0, we get at sine alpha equals v square by L cos alpha. And the acceleration component at 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 the moment of separation of the load is only due to the force of gravity. So at the moment of separation, there is only the force of gravity is acting on the load m, and at equals g cos alpha, as g is directed downwards, g cos alpha, alpha being this angle. So at equals g cos alpha after separation. Rubbing it out. And the velocity of the load at the moment of separation, that is the terminal velocity, which is root over 2gh, as we know, h being this distance, h, which gives us which is equal to this distance also, it is the same, which gives us gl sine alpha, h being l by 2 sine alpha. So we have our velocity, our tangential acceleration after separation, and this equation 2, and the velocity of the body at the same moment is the velocity u of the body at the moment of separation is u is equal to v sine alpha. Let's see this. This is the circle, this is the rod L making an angle alpha, this is L, this is the velocity v, g, this is alpha, this is v sine alpha, that is u, as there is no other force acting on the load M, which gives us sine alpha root over gl sine alpha. We get the velocity of v from here, we add it in, we equate it in this equation number 3. Bring this out. According to the energy conservation law, we have mgl at t is equal to 0. At the initial position, the potential energy is mgl equals to the at t is equal to t, mgl sine alpha at a point when the ball falls on the floor, L sine alpha plus the kinetic energy of the load m, mv square by 2, plus the kinetic energy of the load m, taking y equals 0 as the reference line, m v sine alpha whole square. V sine alpha, from here this is equivalent to mu square by 2, sorry, by 2, the kinetic energy. Rubbing it out. Now solving this equation, we get m gl minus gl sine alpha. We have to find out the mass ratio m by m. Sine alpha minus v square by 2. V is the velocity of the load m, equals m v square by 2 sine alpha, sorry, which equals mv square by 2 sine alpha, which equates to m by m equals 2gl minus 2gl sine alpha minus v square divided by v square sine square alpha. Sorry. Which gives us gl 2 minus 2 sine alpha minus root over gl sine alpha whole square, putting the value of v equal to root over gl sine alpha, the terminal velocity of load m, divided by root over gl sine alpha whole square sine square alpha. In place of v, we put root over gl sine alpha. Now, which gives us gl 2 minus 2 sine alpha minus gl sine alpha divided by gl sine cube alpha. Gl cancels out, giving us the value of m by m equal to 2 minus 3 sine alpha divided by sine cube alpha. On putting the value of alpha equals pi by 6, that is equal to 30 degree, we get the value 4. The ratio m by m equals 4. And the value of velocity u, the velocity of the body m, being v sine alpha, that is root over gl sine alpha. Let's rub it out to make some space. So we got m by m equals to 2 minus 3 sine alpha divided by sine cube alpha equals to 4. And now value of u, which is equal to root over gl by 2 times 1 by 2, that is 1 by 2 root over gl by 2. Therefore, the velocity u of the body m equals half root over gl by 2. Thank you for watching the video. If you like the video, please don't forget to subscribe, share, like and comment in the comment section below. Thank you.